In scenario 1, a swimmer holds a block of mass m at rest in a tank of fresh water with density ρ1, as shown in figure 1 right here. The block is released from rest and accelerates upward with an initial acceleration a1. All frictional forces are negligible. In scenario 2, the swimmer holds the same block at rest in a tank of salt water with density ρ2. ρ2 is greater than ρ1, so the density in the salt water is bigger than the density in the fresh water. The swimmer again releases the block from rest, and the block accelerates upward with an initial acceleration a2. All frictional forces are negligible. So let's get into this final question right here. Indicate whether a1 is greater than, less than, or equal to a2. Greater than, less than, or equal to a2 by writing one of the following in your answer booklet. So I want to justify my answer in terms of all of the forces exerted on the block in each scenario, use qualitative reasoning beyond referencing equations. So they really want me to just use words and my knowledge of physics to say whether the acceleration is greater than, less than, or equal to a2. The acceleration in the fresh water is greater than, less than, or equal to the acceleration in the salt water. So let's think about this here. So what are the forces that are acting on my block when the swimmer lets it go? When the swimmer lets it go, there's a force. I have my buoyant force right here, and I have my weight of the block. The weight doesn't just go away because the block is underwater. So I have to justify my answer thinking about all of the forces. So I would say something like this. Since the mg is the same in both types of water, whether it's freshwater or saltwater, the weight is the same. What about the buoyant force? Well, the buoyant force is going to be greater. The buoyant force is greater in salt water because the buoyant force is greater in salt water because that doesn't look right. Because the density of the fluid displaced is greater. Because the density of the fluid displaced is greater. So the density 2 is greater than the density 1 for the fluid displaced, meaning the fluid that's pushed out of the way of the block. So because the density is greater for that salt water, there's going to be a greater unbalanced force and a greater acceleration. So greater A2, and so there's a greater unbalanced force and there's a greater acceleration. So my answer is going to be this one right here. A2 is greater than A1 because the unbalanced force is greater, the buoyant force is larger. So I described it in words. I didn't really reference the equations. Let's go on to part B. So in part B, I have consider the general case where the block of mass m and volume v is completely submerged in a fluid of density ρ. Starting with Newton's second law, come up with an expression for the acceleration of the block when the block is released from rest. I have to express my answer in terms of these variables and physical constants as appropriate, and I'm going to begin my derivation by writing Newton's second law. So what is Newton's second law? It's the net force divided by the mass of the system is going to be equal to the acceleration. So what is my net force? Well, up here I drew my free body diagram, so I can just use that. So I know which direction the block is going to accelerate. The block is going to accelerate upwards, and so I'm going to do my up forces minus my down forces. So my net force is going to be my up forces minus my down forces. I write it this way because this allows me to manage my signs. I make the direction of my acceleration positive, and then the forces that are opposite my direction of acceleration, I make that my negative direction. And so my equation that I'm going to write is going to look something like this. So I have FB minus mg divided by m is going to be equal to my acceleration. But now notice I have to put it in terms of these variables and physical constants. So what is the equation for the buoyant force? Well, the equation for the buoyant force is the density of the fluid displaced times the volume of the object, of the block in this case, times g, minus mg divided by m is going to be equal to a. And I can simplify this if I want to. I can factor out some g's, and I can, but I'm not going to do that right here. I'm going to leave it just like this question. So that's my answer to part B. Now finally, indicate whether the expression for the acceleration A you derived in part B is or is not consistent with the claim you made in part A. Briefly justify your answer by referencing the derivation in part B. So I want to be specific when I'm referring to my equation right here. So the way that I would think about this is what happens when the density right here increases. If I increase this density right here, that's going to cause this term right here to get larger. And so if this term gets larger, my mg, I said before, is constant. This doesn't change at all. So this stays fixed, and this stays fixed as well. So if this is going to cause my numerator to increase, I'm drawing this bar here to say that, to show that this number is not going to change. So if this density increases, the numerator increases, and if my numerator increases, my acceleration is going to increase because these two are directly related. So if the density increases, if the density of the fluid increases, the numerator, the FB term in the numerator increases. Since mg is fixed, as our density, as our rho Vg increases, our acceleration will increase. This matches what I said. This matches part A. So in part A, we said that where is the acceleration going to be greater? We said it was going to be greater where the density was greater. So because the density of the fluid displaced is greater, in causing that greater acceleration, we can say that this equation that we found in part B is consistent with what we said in part A. And so I referenced my derivation, I connected it back to my claim that I made in part A, and that is my final answer.